Today's lecture is going to be very mathematical. This will be sort of the end of our discussion of fermions, and then next lecture we'll move on to bosons. Of course, we'll come back to fermions a little later in the course, but we're going to close with the Sommerfeld expansion. So we've talked a lot about a Fermi gas at zero temperature, where a lot of simplifications take place. But to understand real Fermi gases, we'd like to know what happens as the temperature goes above zero, because of course nothing's at temperature exactly zero, and we want to be able to sort of check how good of an approximation is T equals zero. If we want to calculate things like the heat capacity, we definitely need to know the dependence on temperature of things like the energy. So while this will be very mathematical, I'm going to try to focus you on particular broad techniques that will be useful to you, later on in this course and kind of throughout your time in physics. And so try not to get too bogged down in the arithmetic. There's a lot of arithmetic that you could get bogged down on. Just keep in mind we're looking at some sort of general techniques, and they are at the end going to lead us to some physical understandings. In the last lecture, we had this expression using the density of states that would allow us to calculate the number at non-zero temperatures. And since the expression on the right is a function of the chemical potential, we would get a relationship between chemical potential and number at non-zero temperatures. So remember, the Fermi energy is defined as the chemical potential at T equals zero. But of course, if we move away from T equals zero, the chemical potential will start to shift some, and we'd like to be able to calculate these things. And if you hear a strange tapping sound in the video, that's the cats running around above me. Hopefully that won't be too distracting. Okay, so we've got this expression for the number. We had this expression for a density of states that pops into there. And to make life a little easier, instead of having to carry around all of these constants, we're going to wrap them up and call them G naught, so that we can see the functional dependence of this integral, right? So the number is just that G naught mess of constants times the integral from 0 to infinity d epsilon of epsilon to the 1/2 over our e to the beta epsilon minus mu plus 1. Right? So in other words, the energy raised to the 1/2 over our Fermi-Dirac distribution. Okay, this looks like an ugly integral, and it'll be the subject of the rest of this lecture, basically. So when we see something like this, there's a couple of techniques that we're going to bring to bear on it. And so to start, I just want to list those techniques so that you can have them in mind as we go through. And the first one is actually a physical insight, right? We want to be able to use our physical intuition to help us with these calculations if we can. And so I brought this picture over from last lecture as well. And this is our picture of the Fermi-Dirac distribution at T equals 0 as compared to the Fermi-Dirac distribution at some non-zero T. Okay. And we said for small t, for T much less than the Fermi temperature, which is to say KT much smaller than the Fermi energy, the change to the Fermi-Dirac distribution is basically localized right around the Fermi energy. Okay. So if we could somehow take this fact, all the interesting stuff is here about the physics, and turn that into something that can help us do the integral, that would be great. And we have done analogous things already in this course where we were looking at, this was back toward the very beginning of the course, looking at the number of configurations for certain systems. And what we found was the formula might look complicated and confusing, but all the action was right around a certain set of configurations, right? So a particular energy, for instance. And so we'd have a distribution that was very steeply peaked, and we could approximate around that peak as a Gaussian, turn everything into a Gaussian integral, which is something we could do, and then we're off to the races. We can actually solve some problems. We want to do a similar thing here of localizing the integral so that we can only worry about the important physics. Now it turns out there's a pretty easy way to localize this integral, right? If we look again, the shape, all of the change takes place near the Fermi surface. I realized as I was responding to some questions on Piazza that there's some terminology I maybe haven't said out loud that I should, because people use it all the time talking about Fermi gases. So this edge at E Fermi, this is often referred to as the Fermi surface. Now, it doesn't look like a surface here because it's not. Normally we're talking about this in the context of some condensed matter system, and there's an occupation edge as a function of momentum. And so I think in the simple case for the 3D gas in a box, our Fermi surface would be a sphere, right? Or actually an eighth of a sphere. Okay. So that's the surface, that's sort of the edge where we go from occupied at t equals 0 to unoccupied at t equals 0. Okay, so I may use the term Fermi surface here, even though it's not really a surface because it's the analogous thing on this plot. Similarly, all of the occupied states below E Fermi are frequently referred to as the Fermi sea. Okay, why? It's a vast expanse. I don't, historical name. So the filled states at t equals 0 are referred to as the Fermi sea, and this edge where you go from occupied at t equals 0 to not occupied at t equals 0 is referred to as the Fermi surface. Okay, so now I can say what I started to say before, which is all of the change takes place near the Fermi surface. But if what we're saying is the interesting physics is the change, right, the change from full occupation to 0 occupation, well, the mathematical word for change is derivative. So if we could take the derivative of the Fermi-Dirac distribution, then we would have a localized function, right? If I take the derivative of this thing, it's going to have a little peak right at EF and fall away to either side. Well, fair enough. We can do that. We've got the Fermi-Dirac distribution here, and we can always integrate by parts. In fact, I heard that Feigenbaum once said the key to theoretical physics is integrating by parts at just the right time. We're going to integrate by parts a lot this lecture. So if we integrate by parts, right, we'll integrate the epsilon to the 1/2 bit, gives us 2/3 epsilon to the 3/2. Here's our Fermi-Dirac. When we plug in 0, the epsilon gives us 0. When we plug in infinity, this term gives us 0. So this whole thing is going to be 0. All right. Now, the fun part, we get to take the derivative of the Fermi-Dirac distribution with respect to epsilon. So we're going to kick a beta out. We're going to get an e to the beta epsilon, right? So the derivative of the bottom is beta times the exponential again. Great. The beta comes out. And since this is 1 over this stuff, we're going to get minus. Integration by parts gives you a minus sign, so the 2 minuses give you a plus over the denominator squared. Okay. So this goes away. Now we've got ourselves something with some localization, right? We've still got this epsilon to the 3/2 that's going to be bothersome, right? Anytime you have a fractional power, it's a good chance it's going to be bothersome in your integral. But we've now got a localized function. Okay? And in particular, it's a function that's localized around epsilon equals E Fermi. And since we're trying to make a low temperature approximation, that's going to be very close to epsilon equals mu. Okay? So this function, and I guess in fact maybe I should say even more carefully, epsilon equals mu is going to be the peak of this thing at non-zero temperatures as well, right? Mu is going to move around. Epsilon minus mu is where this whole thing will be. Epsilon minus mu equals 0 is where this whole thing is maximized. So we're going to have the ability now to expand in 1 over beta mu. right? So for low temperature, beta is big, which means beta mu could be big. 1 over beta mu will be small. Okay. So that's what we're looking at. And what that will mean is we're expanding in distance from this thing, and we only care about distances or positions that are close to the Fermi energy because, again, that's where all the action takes place. Okay, good. So let's drag this integral down here, and we're going to change variables to x, which is beta epsilon minus mu. Dx is beta d epsilon. Great, we had this beta floating around that we didn't want anyway. That'll get folded in to make dx. These guys are already in terms of x. The epsilon is a little bit of a problem, so what do? Well, if we multiply by beta to the 3/2 over beta to the 3/2, so this is going to sit out front. Then we've got beta epsilon. What is beta epsilon? It's x minus, or rather, sorry, when we bring it over, it's x plus beta mu. Okay. So this epsilon will turn into x plus beta mu, and the normalization out front. What else have we got? One of our limits of integration is 0. If I plug 0 in for epsilon, this becomes minus beta mu, so we got a minus beta mu. And if I plug in infinity, it's still infinity, so there we go. Okay, so this integral that we started with has now transformed into this. This doesn't necessarily look like progress if you just look at how chunky is it, but we're now in a position to take advantage of another technique. So the first thing was to say we know physically the important stuff is localized. Let's get an integral that's localized, an integral of a localized function. That's this, right? And just so that you're sure that this is localized, I've mentioned over here, if I multiply top and bottom by e to the minus x, then when it comes into the square, it'll become e to the minus x over 2. This becomes e to the x over 2 plus e to the minus x over 2. In other words, we have 1 over hyperbolic cosine. And if you don't remember what hyperbolic cosine looks like, right, it's only opens up from the origin. So 1 over hyperbolic cosine is going to drop quickly from its peak at 0. Okay, so this is a localized function. Localized around x equals 0. So remember what we were looking at, this x is beta epsilon minus mu, and we said it would be peaked where epsilon equals mu. So great. We've got our integral localized around x. Now, what does that do for us? One thing it does for us, and again, this is something that we did early on in the course when we were looking at these things of like how much energy should be in this subsystem, and we got a very sharply peaked function around a certain energy, and we were doing an integral from, say, 0 to infinity. And then we said, well, wait a second. The value of this function is so tiny at 0, we can just extend the integral to minus infinity, and we're really not changing anything. So we can do something similar here, right? By the time we get to minus beta mu, if we're in the limit where beta mu is much bigger than 1, which is the physical limit we're interested in, by the time we get to x equals minus beta mu, this thing will be tiny, okay? We'll have e to some large power. So we can do the same thing we did earlier in the course. We can extend the lower limit to minus infinity, because invariably we would much rather look at a symmetric integral than an asymmetric integral. Okay, good. So that's our second technique. First, we use some physical intuition to realize we want a localized integrand. Second, we use our expansion parameter, which is to say 1 over beta mu, to look at the extent of the integrand and appropriately change the limits of integration. So here's our new expression. So let's take our new expression for n and push forward. The third technique that we're going to use is expanding in a small parameter. This is something that you've done, I assume, many times at this point in your physics career, where, again, our small parameter is going to be 1 over beta mu, right? Low temperature limit. And so we're going to take the function we don't like, which is something raised to a fractional power, and start expanding it around x equals 0. Okay. Because x equals 0, we said, is where this thing is going to localize the integral. Great. So standard story, Taylor expansion. Probably don't even need me to do this, but I'm going to do it anyway just for completeness. Right? F of 0 is beta mu to the 3/2. F prime, right, drop the 3/2 down at x equals 0. So this is 3/2 beta mu to the 1/2. Okay. So now you're seeing this is going to develop into an expansion in 1 over beta mu. Right? So we divided by beta mu to go from the first term to the second term. Third term, we're also going to divide by beta mu again. So f double prime at 0 is 3/4, right? Plug it in, 3/4 of beta mu to the minus 1/2. Okay. So, and we're just going to keep the first 3 terms for now. You can do more later if you want, but I suspect you're going to feel pretty good after just doing the first 3. Okay. So, what do we have now? We've got n is, right, just bring down 2/3 g0 beta to the minus 3/2 integral of, we've got our localizing function, and we've got our expansion for this stuff to the 3/2. Good. Now we've got integer powers of x. It doesn't guarantee you can do the integral, it just makes it more likely. And you're going to see we have to do a bit of work to get some of these, but yes, we can do these integrals. Okay. So now when you're doing expansion in powers of a small parameter, which again, it's maybe not obvious from the way it's written, but if you look, what do you do from one term to the next? This is an expansion in 1 over beta mu, right? Or said differently, kT over mu. So temperature over chemical potential. And since we're thinking about low temperatures, to make that expansion, temperature over Fermi energy. These are all sort of equivalent to the order at which we're working. And we'll see that mathematically in a minute. So the 0th order term, right? So only keeping the first term, we have, again, the constants from out front, and I've taken the beta mu to the 3/2 times the beta to the minus 3/2, so all it remains is a mu to the 3/2. And since there's no x dependence in the first term, this is just the integral of our localizing function. And if you remember, we got that function precisely by taking the derivative of the Fermi-Dirac distribution, right? This came when we did integration by parts. If you need to be reminded, here we go, right? You can take the derivative of this to verify that this is true, but we just did that to do integration by parts. So great. So we know what this is going to be. This is going to be our Fermi-Dirac distribution. At infinity, it's 0. At minus infinity, it's 1, right? And it's in fact minus our Fermi-Dirac distribution, so we get a 1, not a minus 1. Great. So just the constants from out front pull through. And now I'm going to step back and remind us of what G0 is, because it's going to allow us to rewrite things in terms of the Fermi energy, which is the physically meaningful thing. That's what we want to think in, right? We don't necessarily want to think in G pi over 6, okay? Or G0, which is sort of extra nebulous. So when we re-expand this out in terms of G0, what G0 actually stood for, right? We get G pi over 6. That maybe sounds familiar now. We get the 8m L squared over h squared mu. Sorry, the mu is coming from here, obviously. So the G0 is the 8m L squared over h squared to the 3/2. I'm going to pull the L squared out to become V. You'll see in a moment why. But these things should all remind you of the Fermi energy. And all that's missing is an n. But we've got an n, right? So when we solve this, we get that mu equals, well, these things are going to come out. Well, actually, let's start from the inside. These things are going to come over, right? So n gets the 6 over g pi v. Take it all to the 2/3, and then the stuff that's inside comes out, so h squared over 8m, okay? And that is exactly the T equals 0 result. Right? This is the Fermi energy in the representation, that we had for a gas in a box. And again, let me make this point one more time, just because I am seeing some folks commenting on Piazza that maybe this isn't totally clear. And if a few people are commenting, that probably means a lot of people are wondering about this. This is the formula for the Fermi energy of a gas in a box. Right? So Fermi energy means the chemical potential at T equals 0. We have calculated it for one system so far, right? For a gas in a box. On the problem set, you're going to calculate the Fermi energy for a different system. Okay, so don't necessarily expect it to look like this formula because it's a different system. But it should be the chemical potential at T equals 0. All right, good. So that just means in all of this arithmetic, we haven't messed anything up yet because we did recover the T equals 0 result. Got to push on to get the temperature dependence. Okay, so what do we have next? So we're going to grab the next term. So there's going to be some cancellation between the betas in here. Whoops, I shouldn't click. Between the beta in here and the beta out here, right? So the mu to the 1/2 comes out. We end up with 1 over beta. There's a 3/2 and a 2/3. Those cancel, so we just have G0. Okay. And that x. Well, that integral was easy. I just wrote that it was 0. What's going on? Okay. This expression is even. And again, if that's not immediately obvious, because the way this is written, it's not sort of manifestly even. Remember what I did up above? This thing equals 1 over cosh squared. Cosh squared is clearly even. And I promised myself that as a professor, I would never say something was clearly. What I mean is, if you don't remember what the graph of cosh looks like, look it up quickly and you'll see it's an even function. Or it's e to the x plus e to the minus x. When you swap the signs, that just makes it e to the minus x plus e to the x. Same thing. Okay, so this is an even function. Whoa, getting ahead of myself. So this thing, because it equals 1/4 of cosh, 1 over cosh squared, this is even. When we get down here now, x times an even function, that makes an odd function. So the integral over a symmetric interval of an odd function is 0. Okay, so n1 was easy. n2, not going to be quite so easy. Okay, so n2, come back up. Now we're taking the second term. Okay, feel like a tour guide or something through this integral. Okay, so 3/8, 2/3, that's going to give us 1/4. We got our G0. We got a beta to the minus 1/2 and a beta to the minus 3/2. So we got 1 over beta squared, and the mu to the minus 1/2 is going to pull through. And I just realized you can't actually see this at the bottom of the screen. Great. So the G0 comes down, the 1/4 that I mentioned, the mu to the minus 1/2 pulls through, and then we've got 1 over beta squared. And the x squared comes into the integral. Okay. And magically, I've written the answer for this because we're going to spend a substantial amount of time learning how to do this integral. So for the moment, I will tell you it's pi squared over 3. And I tell you that because I want to get to the physics of why did we do this expansion in the first place. Then we'll go back and see how to take out this integral. Okay. So to order kt over mu squared, right, or 1 over beta mu squared, we have the following result. We're just going to collect up our value for n0 plus our value for n1 plus our value for n2, and that's our approximation to order kt over mu squared. So n is just the sum of those, right? This was just the Fermi energy here. So mu to the 3/2. Sorry, I shouldn't say the Fermi energy. This is the Fermi energy also to the 3/2. Right? If we look back up here, this, before we solve for mu, the constants that go out front in the Fermi energy are to the 3/2. And you know in the Fermi energy, this stuff ends up inside of a to the 2/3. Okay, so 2/3 G naught is 1 over the Fermi energy to the 3/2. And that's also not quite right because I needed this n, right, when I solved. So if I multiply by n over n, now everything except the n out front looks like the Fermi energy. Okay. Good. So this is going to give us n over the Fermi energy to the 3/2. Okay. And then there's this stuff. So here we've got, again, the first term, right? So I have taken this business and I have rewritten it in a more complicated looking fashion. The only thing that really pulled down was the pi squared over 3. Okay, that's still there. Fine. I want this in terms of kt over mu squared because I know relative to the first term, that's how big it is. Okay. And I've got beta to the -2, which gives me kt squared. So I'm going to take this, I'm going to multiply it by mu to the -3/2 to get my 1 over mu squared. But I can't just multiply by mu to the -3/2. I multiply by mu to the -3/2 here and +3/2 here. So the +3/2 is here. And now I've got mu to the 3/2 and I've got a G naught. Great. And I've got a 1/4. I just really want to make this term look like the first term. So I'm going to turn a quarter into 3/8 of 2/3. Okay. So when I rewrite this as n times mu over E Fermi to the 3/2, I've instantly rewritten this as n times mu over E Fermi to the 3/2. I can pull that out of both, and that just leaves me a 1 plus, okay, multiply some things out here, pi squared over 8 because the 3's cancel, kt over mu squared, and that's it. That's all we have. Okay. So you could say we're done, and we almost are. But I want to be sure to make a point about when you do perturbation theory, right? When you do these expansions. This is accurate to order kt over mu squared. And now we're going to solve this thing for the chemical potential as a function of n and t. There's a chemical potential in the second order term. So if we try to solve this thing just as is, we're going to end up with a 4th order polynomial. And there is enough ugly math in this lecture already. I shouldn't say ugly. It's actually, so it's all quite nice. It's just involved. There's enough involved math in this lecture that I don't want to also go down the road of solving a quartic equation. Sorry, I think I said quadratic before. You'll get a quartic equation if you try to solve this for chemical potential. But we don't need to do that because this term already is of order kt over mu squared, which means we can use the 0 order approximation to mu and we won't mess anything up. Okay. So you can think, if I tried to put in a full expression for mu, it'd be like mu0 plus mu2 times kt over mu squared. That's going to end up giving you a higher order term that you don't need to this order. Again, I hope that you've seen perturbation theory done sort of carefully before, which is why I'm waving my hands at it a bit. But if any of that process is unclear, please ask in Piazza. Okay, so the point being, I can just replace this with the 0th order chemical potential, right? And we talked about this up here. We got exactly the result that we'd calculated for the Fermi energy. Another way to say this, though, is by definition, the Fermi energy is the 0th order result, right? The Fermi energy is the chemical potential at t equals 0. So I can just replace the chemical potential in the second term by E Fermi. Everything is still to the same level of accuracy in terms of powers of kt over mu, or powers of 1 over beta mu. Okay, so now we've got this expression, and I'm just going to do one last thing, which is if I've got E Fermi over k, That's our definition of the Fermi temperature. So I can just write this as T over Tf squared. Okay. Now we've got our expression for number, and our expression for number is a bit, well, it looks self-referential because I multiplied by n over n at some point to get E Fermi into the picture, but that's fine. I've now got an equation that I want to solve for mu. I can cancel the n's. That sounds bad. We were calculating n. But again, there's secretly an n hiding in E Fermi, so nothing is really lost here. So I'm just going to bring this to the other side, which is to say this will get raised to the -1 power. The n's have been canceled. There was just a 1 on the other side. So this stuff to the -1 power. Then I've got mu over E Fermi to the 3/2, which means I want to raise the other side to the 2/3. So all of this ends up raised to the -1 times 2/3, or -2/3. That would leave me mu over E Fermi on the other side, just multiply by E Fermi. The chemical potential is E Fermi, what it should be at T equals 0, times, and now we can see the temperature dependence. 1 plus pi squared over 8, T over Tf squared, that's the functional dependence. And maybe I should make that point a little more clearly, right? The constant out front, it's good, you need to know it, but the functional dependence is telling you more about the physics, right? So the chemical potential is going to be quadratic in temperature at low temperatures. Oh, it's all raised to the -2/3. What do we do with that? The whole point of this calculation doesn't work unless this is a small parameter, which is to say we can also do the binomial expansion and just bring the -2/3 inside. So this becomes E Fermi times 1 minus pi squared over 12, T over T Fermi squared. And I just realized up here when I was like kind of waving my hands a bit, I did make a note so that you guys, okay. So if this got confusing in here, take a look at this. It'll be in the notes. Sorry about that. Okay. We've pushed through, we got the result. Yay, chemical potential. It's Fermi energy. It's got quadratic dependence on the temperature, and temperature over the Fermi temperature is sort of what we'd expect. Since you've made it through all of that, give you a short break to meet Echo. Echo, say hi. Say hi, baby. All right, well, she's maybe a little camera shy, but, and now I think she is ready to run around and make noise. All right, here you go, baby. We can use a similar process, in fact, a very similar process, which you will do on problem set 6. It's going to be lots of fun, to calculate the energy of the gas. And what we find is 3/2 n mu to the 5/2 over E Fermi to the 3/2 if you plug in the 0th order value for the chemical potential, which is to say E Fermi. Then this reduces down to 3/5 n times E Fermi, which is what we know we should get at T equals 0. And then we get our non-zero temperature correction. So this is just what comes out of doing the integral. Like I said, you'll get to do this yourself. Now, we want to take the value for the chemical potential that we have to second order and plug this in for mu so that we can get a final value that's good to second order in all ways. Okay. So we need mu to the 5/2. Oh, maybe I've been a little too, right? And we're going to stick this in there. So mu to the 5/2 is going to be E Fermi to the 5/2 times this stuff to the 5/2. And yes, the cats are playing with the light. Good. This raised to the 5/2. And again, the argument is this must be a small parameter, otherwise the expansion doesn't work. And so we can do the binomial expansion here and just bring the 5/2 inside. Okay? So this is our mu to the 5/2. We plug that in. And so the first term here will become, again, the 0th order term we know it ought to have. Multiply it out. This becomes pi squared over 8 n times E Fermi T over Tf squared. And then this last term with the 3 pi squared over 8, n, and then I'm just going to stick another E Fermi here and 1 in the denominator, right? Multiply and divide by E Fermi. That gives me 3 pi squared over 8 n times E Fermi. And with 2 E Fermis and 2 Ks, now this can just become T over Tf squared. Okay. Good, just put these together and we end up with the final answer, which I gave you in the last lecture. Now you know where it's coming from, okay? N times E Fermi times our 3/5 plus the temperature dependence, which again is quadratic in T. Okay. And the real payoff here, because we don't generally go around measuring the energy in a Fermi gas, although in fact in ultra-cold atoms experiments you can do this, but for example, the electrons, conduction electrons in a piece of copper, you can't just measure the energy of the electrons, but you can definitely measure their heat capacity. Okay. And so to calculate the heat capacity, just do the standard thermodynamics thing, right? It's the rate of change of the energy with temperature. And when we take the temperature derivatives up here, we're going to get pi squared over 2 n times E Fermi over T Fermi, right? Because that's the units we should have in energy per temperature. And then it's going to be linear in T, right? So T over Tf. And if we just shrink this down a bit more, right? E Fermi over T Fermi is just K. So this looks kind of like, at least vaguely reminiscent of what the heat capacity should be for an ideal gas. And by should be, I mean a classical ideal gas, right? It's proportional to Nk. We have treated these fermions as structureless particles, which is certainly correct for electrons and a very good approximation for lots of other things like nucleons or cold atoms. And so it should be 3/2 Nk in the high temperature limit. And now you can kind of, look at this a bit and say, well, this is certainly bigger than 3/2, so this answer will not be good even up to T equals Tf. That's not surprising because we know that this is an expansion in 1 over beta mu, or equivalently or nearly equivalently T over Tf. So if it's an expansion in T over Tf as a small parameter, well, this won't be good up to T over Tf equals 1. But now for many systems where we're well below the Fermi temperature, we have a way to actually understand the specific heat, the heat capacity. We're going to go through these integrals in a little more depth, though I'm going to go a bit faster than I was earlier. So again, as always, pause if things are going by too quickly, check the arithmetic yourself, make sure it makes sense to you. So we're looking at these integrals in part because they're of a type that's going to come up repeatedly. It'll come up again with bosons. If we try to do some deeper things with fermions, it'll come up again. So let's just take a look at them now. So we had this integral before, and I told you it's pi squared over 3. And yeah, how do we do this ugly thing? How does this, which has nothing to do with circles, end up being pi squared over 3? Okay, so I've given you sort of 2 hints here about how we're going to attack this thing. And this is somewhat good advice for any integral that you come upon that you don't know how to do off the bat. First, look for symmetries. Okay. This x squared is even. We saw that this is really 1 over cosh squared, so it's even. Overall, the integrand is even. That's going to allow us to change the limits of integration in a way that may help us. It's not guaranteed, but in this case it will. And then we know that this thing is the derivative of the Fermi-Dirac distribution. Well, it's something that we can integrate. And in a sense, that's all we need to know we could do integration by parts. So another maybe kind of rule of thumb or intuition that you might have about integrals is if I have something awful, which is to say not a polynomial, right? Exponentials, trig function, something like this, multiplied by a polynomial, there's a chance I can integrate by parts repeatedly and just get rid of the polynomial part. There's no telling what's going to happen over here, right? You need to be a bit lucky with this, but it could be the case that you can integrate by parts repeatedly and just take the polynomial out with derivatives. That's going to help us here. Okay, great. So we've got this integral again. What are we going to do? The first thing is take advantage of the fact that it's even. This is going to be 2 times the integral from 0 to infinity. Same stuff because it's even. And next, we're going to integrate by parts because we know we can, and it may help. So what do we get? The 2 hangs out up front. We're going to integrate this thing to get minus the Fermi-Dirac distribution. 0 to infinity again. At 0, this kills it. At infinity, this kills it. So that's all 0. And when we take the derivative of this and have a minus sign for the integration by parts and a minus sign here, we get plus 2x times the Fermi-Dirac distribution. Okay. This is the type of integral that we'll see often. Okay. So secretly what we've done is we've transformed this into a form we already know, except you don't already know it. I do, but soon you'll know it. And again, it's one that you'll want to know because things like this will come up repeatedly in StatMech. So when we want to deal with these kind of integrals, and there's a whole class of these things, there's a trick. And the trick is, for positive x, we can take this, multiply it by e to the minus x over e to the minus x. Okay, that doesn't have to be positive x yet. Okay, that gives us an e to the minus x over 1 plus e to the minus x. The part where we need x to be positive is, I'm going to take this and pretend it's e to the minus x times 1 over 1 plus e to the minus x, and e to the minus x is less than 1 here, so we can treat this like the sum of an infinite geometric series. Okay. So this is another sort of mathematical theme that we saw many lectures ago for the partition function of a harmonic oscillator. It's coming back again. So, except now we're doing the reverse, right? We've got something that looks like the value of this sum. We're going to turn it back into the explicit sum. Why would we do that? We would do that because something times e to the x, or a power of e to the x, sounds way better than something times 1 over e to the x plus 1. So let's use this. Our integral is going to become the integral of x times this thing becomes an infinite sum, right? And I don't want this to be m plus 1. That's messy. I'm also going to do the thing that you should very carefully prove in mathematics that you can do, but you can in this case, which is swap the order of integral and sum. The sum pulls out, and I'm going to take an extra minus sign so I can re-index the sum. Right? So the m equals 0 term is actually an e to the minus x. So if I just re-index, I'll get e to the minus mx, starting the sum from 1, and then this would be minus 1 to the m minus 1, but I don't want that, so I'll just pull an extra minus sign out, and whether it's m plus 1 or m minus 1, same story, so great. So this is minus, we've got the sum, the minus 1 to the m sits out front of the integral, and now our integral just has x times e to the minus mx. This is exactly the case I had in mind before when I said if you've got stuff that's not polynomials times a polynomial, integration by parts is probably your friend. This is a great case, right? Because we can integrate e to the x for the rest of the year, right? Always going to get an e to the x back. So if this was x to the 400, right? We're going to have to integrate parts a number of times, but eventually we're going to knock that x to the 400 down to just a 1. This will still be e to the x, and we can do the integral. Thankfully, it's not x to the 400, so this will go quickly, right? Just integrate by parts. This guy gives us a negative 1 over m when we integrate it. Bring the x along. 0 to infinity, this is going to go away again, right? At 0, this is 0. At infinity, this is 0. So that term's gone. Minus sign for integrating by parts makes us a plus 1 over m. And now we're just integrating. After we take the derivative, the x is gone. We're just integrating e to the minus mx. That gives us another factor of negative 1 over m. And when we plug in the limits, the lower limit is the one that equals 1. So negative, negative, we get a positive. This just becomes 1 over m squared. Okay. Good. So we've integrated by parts. We've got a value for this thing. Nice. Now, don't forget it's inside of a sum. Okay. So the integral is minus the sum of negative 1 to the m over m squared. And I've written this out just, it's nice to look at the explicit sum sometimes. May give you an idea of how to approach it. 1 minus 1 over 2 squared plus 1 over 3 squared minus 1 over 4 squared, right? I could rewrite this as 1 over 1 squared to make it all look good. And in fact, if I did that, this would now look reminiscent, not exactly the same, but reminiscent of something called the Riemann zeta function. And that's probably behind my head. There we go. Okay, so the Riemann zeta function is defined as the sum from m equals 1 to infinity of 1 over m raised to the s power. So zeta of s is the sum on 1 over m to the s. So this looks, almost like the sum of 1 over m squared, except the signs are alternating. Well, I want to connect this to the Riemann zeta function, in part because the Riemann zeta function is so cool, and in part because everyone else does it. But also there's some neat tricks for calculating the Riemann zeta function. So we're going to relate this sum to the Riemann zeta function. And how will we do that? I'm going to go make sure the cats aren't destroying my house, and then we will take a look at that. House is still intact. The kittens look a little alarmed and a little guilty, but we'll keep going. So we want to make our sum, which is alternating, look like the Riemann zeta function. And the way to do that is, well, just claim it's the Riemann zeta function. But we need to fix it up, right? So this is going to have positive values on these even terms. So we just need to subtract off the even terms. And in fact, we need to subtract off 2 times the even terms, right? Subtract it once, we'd have a hole here, subtract it twice, now we get the minus signs we wanted. And since this is just 1 over 2m, all of it squared, that's just a quarter of 1 over m squared. Pull the quarter out, this becomes a half of sum on m of 1 over m squared. This thing is the zeta function of 2. And now this thing is also the zeta function of 2. So we've got zeta of 2 minus half zeta of 2. We got at the end 1/2 zeta of 2. Okay, great. Now we've got this in terms of something that maybe you just met for the first time in this lecture. So the original goal was to do this integral. We turned it into 4 times this integral. And now we've found that this integral is equal to 1/2 zeta of 2. So the original integral is 2 times zeta of 2. And, strange but true, this zeta function, which is a sum of 1 over integers squared, turns out to be equal to pi squared over 6. We will actually see this in a couple of minutes where that comes from as well. But again, for the moment, you could plug it into Wolfram alpha if you wanted. Wolfram alpha will tell you it's pi squared over 6. Your favorite number theorist friend will tell you it's pi squared over 6 and probably be very excited about that fact. But okay, so we get the integral as pi squared over 3. And again, I said this form is going to come up a lot. And in fact, it's going to come up soon because when we go to bosons, we're going to be doing integrals of this form, except not the Fermi-Dirac distribution, the Bose-Einstein distribution. So I'm going to let you take a few minutes and see if you can follow through the same steps that we did for the Fermi-Dirac distribution to get a value for this integral. Were you able to work through it? Okay, I hope so. Let's take a look. So we're doing this integral. We're going to start with the same trick, multiply top and bottom by e to the minus x. So that turns it into this integral. Same trick again, we're going to write this as a geometric series, except since it's 1 minus e to the minus x, we're not going to have that alternating sign, right? So this is going to be a sum on the integral of x e to the minus x. We already know this integral is 1 over m squared. And again, because of this sign, we don't have the minus 1 hanging out here. So this is just zeta of 2, or as its friends know it, pi squared over 6. So I am not going to walk you through these, but if this sort of thing has been fun for you, you can take this a step further and actually find generic formulas for these things. And I've kind of given you the roadmap for it, right? It looks a lot like the integrals we've been doing, except it's x to a higher power. If you integrate by parts a lot, you can come up with a general formula for this. So good, have fun with that, or don't. Well, this lecture has been pretty mathematical. For those of you who are still having fun, I want to give you just a last little bonus. We won't be needing this technique or anything. I just think it's pretty cool. Zeta of 2 equals pi squared over 6. That makes no sense. Okay. Proving this is what made Euler famous. Now, if you know anything about the history of math, Euler is famous for 1,000 different things. This was big even by Euler standards. Okay. How did he do it? It's actually, you can see the answer down here. We're going to get there in one page. So first, Taylor expands sine of x. Okay, this is something you know how to do. And now divide it by x. So we get the Taylor expansion of sine x over x. Okay, gets rid of that x out front to give us just a 1. Fine. Why do we Taylor expand this? Well, the roots of this function are at, well, the roots of sine of x, right? Except at 0. Because if you have seen this function before, it actually has a well-defined limit at x equals 1, or sorry, at x equals 0, and it's 1. Okay. So this does not have a root at x equals 0, but it has roots everywhere else that sine has roots, which is to say positive pi, negative pi, positive 2 pi, negative 2 pi, right? Plus minus 3 pi, 4 pi, all the integer pi. Sine of x has a 0, has a root. Now, if you remember from polynomials, you can always write a polynomial in terms of its roots, right? So if these are all the roots, then this thing can be written as x minus pi, x minus negative pi, x minus 2 pi, and so forth. And the only thing that's missing is the overall normalization constant. Okay? But we know the constant term in this Taylor expansion is a 1, right? So whatever, when we multiply all these things, we'll have terms that look like x squared, x cubed. The constant term is going to come from multiplying all of the constants together. So we can get to 1 by just dividing everything by its root. So x minus pi, I'm going to actually divide by negative pi to swap it in order. So I get 1 minus x over pi. Divide by negative pi here. Negative pi. So divide by pi here, get 1 plus x over pi, right? Divide by negative 2 pi, get 1 minus x over 2 pi, and so forth. And I've written these sequentially because we get plus and minus for every root, but I've also written them sequentially because now this is a binomial conjugate, which is to say when I multiply these two, I get 1 minus the second term squared, right? The cross terms here cancel. So 1 minus x squared over pi squared. Do the same thing here. I get 1 minus x squared over 2 squared pi squared. If I take the next two that weren't written here, I'll have 1 minus x squared over 3 squared pi squared. Okay, 1 squared, 2 squared, 3 squared. Maybe Euler was onto something. Right, so now we've written this thing as a product. And if we were to start doing the product out, we engineered it so that we'd get 1 times 1 times 1 times 1. The constant term is a 1, as it should be. The x squareds can only come from one of these terms times 1 times 1 times 1 times 1, right? This term times 1 times 1 times 1 times 1. So we will just get this plus this plus this plus this, right? So 1 minus, what do all these terms look like? Every term has an x squared over pi squared. That can go out front. And again, this is 1 over 1 squared, 1 over 2 squared, 1 over 3 squared. So when we start doing the product out, we'll get 1 minus x squared over pi squared, sum on the integers, 1 over integer squared, plus some more stuff. And we're going to stop because we got what we wanted. There's zeta of 2. Now, all we have to do is compare this to the Taylor expansion. Each of these should give us a correct expansion for the function. So here, the coefficient on x squared is negative 1 over pi squared times the sum 1 over the integer squared. Up here, it's minus 1 over 3 factorial, so minus 1 over 6. This is zeta of 2. Just solve for it. Multiply both sides by minus pi squared, and there it is. Zeta of 2 is pi squared over 6. And now you can say you've really seen every step of getting a simple numerical factor in front of the t squared dependence in the heat capacity. But, like I said, it wasn't just about getting that one numerical factor. Right? This part was just about having a little fun with math. But the rest of the lecture, the focus is really on the techniques that we use, because they will be general techniques that you find useful in mathematical physics throughout your time in physics.